Hi, this is Professor Stugard, and in this video we're going to be discussing the gradient. The gradient is a fairly simple thing to calculate, but we are going to see it show up in many different contexts across vector calculus because the gradient is actually an incredibly powerful and useful tool when we discuss things about our different surfaces, or as you're going to see, things like vector fields later on. Now, again, to calculate the gradient, it's fairly simple. If I'm given a function of two variables, x and y, the gradient is just my partial derivatives put together in a vector. So the partial with respect to x and the partial with respect to y basically put together. And the way we denote our gradient is by an upside down triangle in front of f. This is called the del operator, and you're going to see this del operator show up a ton as we work our way through vector calculus and multivariable calculus. The reason it shows up so often is that it's just incredibly useful notationally and is very much applicable to this idea of our gradient. Now, you might see the gradient called the grad f, and again, that shows up in some older textbooks. So you might just see that as well. But again, all it really means when we take the gradient is we're taking the partial derivatives with respect to each one of the variables and putting them in vector form. Now, you will see quite frequently the standard basis form of this as well, where again, if my function is f, then my gradient is going to be the partial of f with respect to x in the I-hat direction and the partial of f with respect to y in the j-hat direction. So again, you might see these two different notations. They mean the exact same thing, and they all get simplified with our nice, neat del operator notation with the upside down triangle in front of f. The nice part is the gradient concept can be extended to higher dimensions as well. So if I have a function with three variables, x, y, and z, well then the gradient is just going to be the partial with respect to x, the partial with respect to y, and then the partial with respect to z. And it turns out we can actually apply the concept of the gradient to however many variables we want. And in fact, applying the gradient to functions of dozens, if not hundreds of variables is actually a very important part of machine learning. But let's go back to directional derivatives for a minute. Now, if my function is differentiable, then we saw earlier that the directional derivative is going to be in the direction of some unit vector, u, given by ab, and we had our formula. Well, as you mentioned, my formula is the sum of products, which means I can rewrite it as a dot product. And then it turns out that, well, if I take those first components, since they're the partials, and put them into a vector form, well, really, I can represent that entire idea with just my gradient notation. And then, obviously, with my unit vector u, my directional derivative now is written very simply as the gradient of f dot u. We're going to apply that idea to several other concepts as well, but first, we need to go back to our vector functions. So if you remember, when we're talking in 3 space, we represent our lines and curves as vector functions. Now we can do this in 2 dimensions or 3 dimensions, but again, typically in Calc 3 and multivariable calc, we're working in 3 dimensions. And so again, the idea is that basically it's a parametric equation where you have your equation for x in terms of t, your equation for y in terms of t, and your equation for z in terms of t. Now with our vector functions, if we want to find the derivative of a vector function, we just take the derivative of each component one by one. So if I have a vector function in terms of, well, just 2 variables, x's and y's, then my derivative, r prime, or dr dt, is just going to be the derivatives of each component one by one. So the derivative of x with respect to t, and the derivative of y with respect to t. And when we take that derivative of our vector function, we call that the tangent vector. So dr dt is our tangent vector. So if I was asked to find the tangent vector for this particular function, r of t is t squared, comma sine t, comma e to the t, Well, to find the tangent vector, we just go component by component. So the derivative of t squared is 2t. The derivative of sine is cosine, and the derivative of e to the t is e to the t. And that's how we find tangent vectors. It's actually a pretty simple concept, and kind of similar to the gradient, I suppose. So let's go back to the chain rule, which we saw a few sections ago. So we saw that if we're given a function, z of two variables, but I can write my two variables x and y as functions of t, well, then my chain rule was dz dt is really the partial of z with respect to x, dx dt, plus the partial of z with respect to y, dy dt. And, oh, here we have again, we have a sum of products, which means if I put these in vector form, I can represent this with a dot product. Except when I look now, well, my first vector now, partial of z with respect to x, partial of z with respect to y, that's my gradient. And the dx dt, dy dt is my tangent vector. And so I can actually simplify the chain rule with really neat notation as the gradient of f dotted with dr dt. And this is something we are going to definitely see again later on in this semester. Now, a quick word about notation. Like I said, we can extend the gradient to as many variables as we want. Again, typically we're going to stick to either 2 variables or 3 variables. And the idea is that I can use this notation where I represent my variables as a vector itself. So my x vector is the vector composed of each of my variables. So again, x and y for 2 variables, x, y, and z for 3 variables, or, and admittedly this shows up more in linear algebra, but we can generalize our proofs this way too. No matter how many variables I have, if I have lots of variables, dozens of variables, I can represent each of my variables, again, as that vector x, and then just write each one as x1, x2, x3, all the way up to xn. Time for an important theorem about our gradient and how it relates to the directional derivative. So the first part of this theorem says that the maximum value of the directional derivative, which really means it's the maximum rate of change, right? My directional derivative is a measure of the rate of change. It's a derivative rate of change. So the maximum of the derivative is a maximum of the rate of change. So the maximum rate of change of my function is going to be given by the magnitude of the gradient. And again, that might not be completely obvious why, but we'll go through a proof, don't worry. And then it's going to occur in the direction of that gradient. So my maximum rate of change is going to occur in the direction of my gradient, which in the case of a directional derivative is the same direction as u. And it's actually that last implication right there that forms the basis for a lot of machine learning optimization algorithms. So let's actually take a look at what this is saying. So remember, we defined the directional derivative as the gradient of f dotted with u. But it's a dot product, which means I can apply the dot product theorem, which means it's really equal to the magnitude of the gradient times the magnitude of u times cosine of theta, where theta is that angle between the two. Except we already know that the magnitude of my unit vector has to be 1, which means my directional derivative can actually be defined as the magnitude of my gradient times the cosine of theta being, again, that angle between my unit vector and the gradient. Now, this is important enough that this almost is considered a theorem by itself, this little formula here, because the implications of it really is what gets us to the rest of the theorem. Because we know that the largest value of cosine has to be 1. Cosine is bounded between -1 and 1. The biggest value it can be is 1. And that occurs when theta equals 0. Now that means that the largest that my directional derivative can be is going to be the gradient of 1. Otherwise, my cosine of theta is something less than 1, which is going to scale it smaller. The biggest it can be is, well, 1, which means the biggest my directional derivative can be is whatever that gradient of f is going to be, because it'll be the gradient of f times 1. And is going to happen when theta equals 0, which means it has to be the same direction as my gradient. So how do we actually use this in practice? Well, for example 2, let's say that we have surveyors who determine that the elevation of a hill can be modeled by this particular formula. Z equals 200 minus 200ths x squared minus 400ths y squared, where Z is your feet above sea level. And my question I want to answer is, what is the maximum rate of change at the point 40, 60? Let's make sure we understand what's going on first with our function. And so this model puts the top of our hill at the ordered pair 0, 0 with a height of 200 feet. And the point 40, 60 then means I'm moving 40 feet in my x direction, so 40 feet away in the positive x direction, and 60 feet away in the y direction. And again, this formula gives us a shape called an elliptic paraboloid in 3 dimensions. So there's my function. And again, if I want to find that maximum rate of change, it's all related to the gradient. So the first thing we're going to do is calculate the gradient. But this should be fairly simple, because when I take it with respect to x, well, there's only one term that has an x in it. And we know the derivative of x squared is 2x, which is going to make this minus 400ths x. And similarly, there's only one term that involves a y. And we know the derivative of y squared is 2y, so that's going to give us a partial with respect to y of negative 800ths y. So we have our gradient. We evaluate the gradient at our ordered pair. In this case, plug in the values 40, 60, which gives us corresponding values of negative 1.6, negative 4.8. And then my maximum rate of change is just the magnitude of that vector. So if I find the magnitude by, basically applying the Pythagorean theorem, I get that my maximum rate of change is approximately 5.06. And we know that that maximum rate of change is going to occur in the same direction as my gradient. And from that point 40, 60, where x and y are both positive, my gradient is pointing in the negative direction. It's actually pointing back towards the top of the hill. And that should make some intuitive sense as well. The maximum rate of change, if I want to get steeper faster, I need to go up the hill. I need to go towards the top of the hill. Now for some more facts about the gradient that are going to be very useful. So the gradient at a point is going to be orthogonal to the level curve at that point. Now, what that also means is that the gradient at a point is orthogonal to the tangent at that point. And let's take a look at why that might be by first looking at an example. So let's say I'm given a surface z equals x squared plus y squared, or f of xy is x squared plus y squared, my function of two variables. I want to graph the level curves, which you already know how to do, and then find the gradient vectors at several different points. Well, let's start with the level curves. Again, level curve means you're just setting it equal to some constant, so setting it equal to some k. But if k equals x squared plus y squared, these are the equations for a circle, right? Where k is really going to be equal to your radius squared. So when I plug in different values for k, like 1, 2, 3, 4, 5, 6, 7, 8, and 9, I'm just going to get a bunch of concentric circles. Now, we can see, again, if we're just kind of evaluating what's going on with our level curves, and from our original, work that we did, they're closer together here, which means it's getting steeper. They're much further apart here, which means it's not as steep. And again, that matches exactly what our actual function looks like. But we want to find the gradient and evaluate the gradient at several points and look what goes on with our level curve. So first I need to find the gradient, but this is about as easy as it comes, because again, it's the partial with respect to x. There's only one x term. So the partial with respect to x is 2x. The partial with respect to y is 2y. So there is my gradient right there. It's 2x, 2y. Fairly simple. Now I want to evaluate my gradient at those different points. So we'll start with the ordered pair 1, 1. But clearly, if I plug in the ordered pair 1, 1, 2 times 1 is 1, 2 times 1 is, 2 times 1 is 2, 2 times 1 is 2, so I get the vector 2, 2. And if I start at my ordered pair 1, 1 and move in the x direction 2 units and the y direction in 2 units, well, there we go. And hopefully we can see that clearly that is making a right angle here with the tangent. It's making a right angle with my level curve. Now, note my vectors are scaled a bit smaller to fit here. If that actual vector was 2, 2, it would be twice as big. But to make sure everything kind of fits on this picture, there we go. And when we do the next one, my ordered pair 0, 1, again, plug in a 0 for the x, it gives me 0, plug in a 1 for the y, that gives me 2. And if I go to that ordered pair 0, 1 and try to graph my vector 0, 2, it's going to be straight up and down. And again, you're getting a right angle with the tangent, or a right angle to the level curve at that particular point. Similarly, when I check the ordered pair 1, 0, I'm getting my gradient vector to be equal to 2, 0, which again is going to point just along my x direction, again making a right angle there with my tangent or with my level curve. And lastly, if I plug in the point -1, root 3, my gradient vector is -2, 2 root 3, which again is going to be pointing away at a right angle to my level curve and a right angle or orthogonal to my tangent at that point. Now, the process we're actually doing right here is called making a vector field. And if you've taken differential equations, you might have seen vector fields already. Vector fields are going to play an incredibly important part in chapter 16 when we get there, and we're going to do this process again. So it's nice to see the gradient show up here and kind of get an idea and let you know that, well, we're going to be doing the same process later on as well. So now that I see it in action, well, what does it really mean? And how do I know that that's the case? Well, how do I know that the gradient at a point is going to be orthogonal to that level curve at that point, regardless of how many variables we're dealing with? Well, we're going to go back to the idea of a level surface. So we saw this very, very briefly in earlier units, but a level surface is basically going to be where the x, the y, and the z are all on one side of my equation, and then it's just a constant on the other side. So again, this is still a surface in 3 dimensions. I still have 3 variables, x, y, and z. It's just that the way I have it written as an implicit function with every variable on one side. The next thing I want to consider is a curve that's going to be on that surface. So I need to give that as a vector function, r of t, and this curve is on my surface everywhere. That means it absolutely lies on my surface. No matter where I graph my curve, that curve is still on the surface no matter where. Which means that if I were to plug in my vector function into my surface, well, that's got to still be true because it's got to exist there everywhere. So for every value of t, well, my curve is still on my surface, which means it still needs to satisfy the equation of my curve. That's what it means, right? My equation for the surface is an equation that relates every ordered triple to a certain set of rules, and my vector function has got to obey those rules as well if it lies on my surface. But I can apply the chain rule and differentiate both sides here. Now, when I apply the chain rule to something with 3 variables, well, we should hopefully remember how to do this. We just basically apply to that 3rd variable as well. So partial f with respect to x, dx dt. The partial with respect to y, dy dt. The partial with respect to f, or the partial of f with respect to z, dz dt. And then, of course, when I differentiate any constant on that right-hand side, it's going to equal 0. But again, this is a sum of products, and we already talked about the fact that when I apply the chain rule, I can write this as a dot product. And so I get the gradient of f dot dr. But we know by the dot product theorem that if the dot product is 0, that means the gradient and the tangent have got to be orthogonal to each other. They have to be at a right angle, which, again, we saw that actually occurring when we were making our vector field, when we were graphing with those level curves. We saw that the gradient was absolutely going to be orthogonal to our tangent vector, and this is why. The really nice part is that I can actually use this fact to find tangent planes even easier than usual. So let's say I want to find the tangent plane to this surface z equals x cubed minus y squared plus 7 at a particular point. If I'd make my first step to write this as a level surface, meaning that I just move the z to the other side, move the z to the other side with the x and the y, I'm going to be able to then find the gradient and use that as my normal because I know it's going to be orthogonal. So if I just subtract that z from both sides, I get x cubed minus y squared minus z plus 7 equals 0. Take the gradient, and again, really easy in this one, term by term, just, again, doing polynomials. But again, take your time, pause the video, do it yourself, make sure you're getting the same answers as me. And then what we're going to do with our gradient is evaluate it at that point. Because when I evaluate it at that point, it's going to give me my normal. So, plugging in a 1 for the x, a 2 for the y, a 4 for the z, not that there's any z's to actually plug it in for. We plug it into my gradient vector. It simplifies to the vector 3 minus 4 minus 1, which is now my normal vector. And there we go. To find the equation of a plane, I just need its normal and a point. I have my normal, I have my point. We plug it into our formula for finding the equation of a plane. Plug in all the values, simplify term by term, and again, pause the video, do it yourself. Make sure you're getting the same answer as me. And hopefully at the end, we get 3x minus 4y minus z equals -9. And again, it gives us another great tool for finding tangents and tangent planes now that we understand what the gradient is. All right, so that's all I wanted to talk about with the gradient in this particular video. There is a lot here. You may have to watch this video more than once to pick up on everything, but take careful notes. Let me know if you have any questions about this. And as always, feel free to point out any mistakes or anywhere you might have been confused as well. That way I can hopefully make these videos better for you in the future. Good luck with your homework and take care.